So two things we're doing today. We're going to do one more of these, finding least degree polynomial function, and the other is Rene Descartes' rule of signs. You all may or may not be familiar with or have heard the name Rene Descartes. He did a lot in mathematics. He did actually a good bit in philosophy as well. One of the philosopher, or kind of, for multiplication or division, or multiplication, addition, subtraction powers, but not much outside of that. One of the philosophical things he has become known for is, I think, therefore I am. He actually coined that phrase. I think they were really trying to get a foul on you for the. Not a foul against you because you did what you're supposed to. The other kid just happened to run into your elbow or arm. And the ref was 100% on your side. So this is the first one we're going to do today. Really the only one of this type we're doing, because I do want to walk through one more of these so we can see this. Now this one here does have an imaginary and irrational term. So because of our irrational conjugates theorem and complex conjugates theorem, since 1 plus I squared root of 5 is the solution, 1 minus I squared root of 5 is also. Now our first step is to get these equal to 0. So the first thing we can do with x equals 3 is to subtract 3, telling us x minus 3 is 0. And that's it for that one. The next one, we're going to get it equal to 0. So we'd minus 1 from both sides. Telling us x minus 1 is equal to I square root of 5. And then we would subtract I square root of 5 from both sides, telling us x minus 1 minus I square root of 5 is equal to 0. And lastly, we'll do the same thing with the last one here, minus 1, telling us x minus 1 is equal to negative I square root of 5. Then we'll add I square root of 5 to both sides, telling us x minus 1 plus I square root of 5 is equal to 0. So the first thing we had to do for this one here is to get each of our solution back into factored form, or in other words, get them equal to 0. Then multiply them together. That's 4.4, well, it's 4.1, 4.2, and 4.3. Yeah. Both of y'all turn that one in.
Yeah, I had it like almost ready. That's when he lost his body. And then I just had to redo it.
Yep. So y'all done that one. We can go over that before the end of the hour. At this point here, we're just going to multiply our two terms with I and square root first. The distributing property with x, multiplying through by x, is kind of nice. X times x is x squared. X times negative 1 is negative x. X times I squared of 5 is xi square root of 5. We'll do the same thing with negative 1. Negative 1 times x is negative x. Negative 1 times negative 1 is plus 1. And negative 1 times negative I squared of 5 is negative I square root of 5. And lastly, distributing our I, negative I square root of 5. Well, negative I square root of 5 times x is negative x I square root of 5. Negative I square root of 5 times negative 1. Negative negative makes positive I square root of 5. And lastly, we have negative I square root of 5 times I square root of 5. Well, luckily, if we wanted to put this in the calculator, we could. Negative I square root of 5 times I square root of 5, we get 5, positive 5. And that gives us all this here. Questions on how we got to this point here? Now at this point we're going to combine like terms. Well, xi squared root of 5, negative xi squared root of 5 is 0. Negative I squared root of 5 and I squared root of 5 is 0. So the only terms we have left are x squared. Our negative x minus x is negative 2x. And 1 plus 5 is plus 6. And last but not least, we're going to distribute this here. So we'll multiply through by x, which would give us x cubed minus 2x squared plus 6x. Then we can distribute the negative 3. Negative 3 times x squared is negative 3x squared. Negative 3x times negative 2x is plus 6x. And negative 3 times 6 is negative 18. And when we combine like terms, we'll have x cubed minus 5x squared plus 12x minus 18. And that there's our final answer. Questions on this here? Most of this is just multiplying out and seeing what our polynomial function is. We do have others, but this is the last part of chapter 4 we're covering. There are other sections, but we don't have time for them, and we're not going to cover them. Now, Descartes' rule of signs is something that is kind of helpful, because what it tells us is that if we let f of x equal, all this here is just a polynomial, or polynomial functions we've been solving, with real coefficients, then the number of positive real zeros of f is equal to the number of sign changes of the coefficients of f of x, the number in front of x, or is less than it by an even number. So if the number of sign changes is 4, it could be 4, 2, or 0, because we can keep subtracting 2 till we get a negative number. The number of negative zeros is equal to the number of sign changes in the coefficients of f of negative x, or is less than it by an even number. So the same thing. It could be 4, 2, 0, or 3, 1. And we go that way. And then the really we could say complex zeros are the missing ones. Whichever ones are missing. And that'll make more sense, especially when we start looking at this. So, determine the number, or the possible number of positive real zeros, negative real zeros, and imaginary, or complex. So to figure out the number of positive zeros, we take the function f of x, this here, and count the number of sign changes. Count the number of sign changes. So if we look at this here, from x squared, or not x squared, x to the 6th to x to the 5th, does the sign change? Because the sign in front of the x to the 6th is what? Positive. Sign in front of x to the 5th is, so did it change? It went from positive to negative, yes? So that is one sign change. X to the 5th to x to the 4th, it goes from negative to, so did the sign change? So that is 2 sign changes. X to the 4th to x to the 3rd goes from positive to negative, so that's a third. x to the third x squared goes negative, negative, so it does not. X squared to x. So the number of sign changes that we have is 3. So the number of possible positive real numbers, so the number of possible positive numbers, that's such a tongue twister, is 3, or 2 less than it. Well, 3 minus 2 is what? 1, yes? And we can subtract it again. 1 minus 2 is negative 1. But you can't have negative number of solutions. So for this here, the possible positive real zeros is either 3 or 1. That's it for that part, yes. And this seems a little superfluous. It doesn't seem really helpful. But the reason this is helpful is because if I find 2 values of x that are positive that work for this, that means that there should be one more positive 0. It helps us figure out what kind of zeros we're looking for. And especially if we combine it with our positive or our rational zeros theorem, we can start eliminating out other choices, finding the solution. Now the next part, we need to find the possible negative real solutions. And what we do for this here is we take f of negative x. And what that entails is that we're going to replace every x with negative x. So the first one would be negative x to the 6th minus 2 times negative x to the 5th plus 3 times negative x to the 4th minus 10 times negative x to the 3rd minus 6 times negative x squared minus 8 times negative x minus 8. So we have all this here. I will tell you this now, simplifying these is going to be easier than what you might think. Because if we look at this here, I'm going to look at this one all the way over here first. 6 times negative x squared. When we multiply a negative by itself, we get a what? Positive. So what that's telling us all the way over here is that our negative x squared is just going to be x squared, because negative x times negative x is positive x squared, yes? And we multiply it by our negative 6, telling us that we just have negative 6x squared. The one after it, negative 8 times negative x, well, the negative and negative make a positive 8x, and we have our minus 8, because it's just still minus 8. So when we multiplied the negative x by itself, it became positive x squared. If I multiplied negative x by itself one more time, it would go from positive to negative. So we would have x cubed, but now it's negative, and our negative times negative 10 would make it positive 10. Well, this became positive, the cubed became negative, or stayed negative, and our negative made it positive. Our 4th power, well, this is just going to be x to the 4th. And really what I'm getting at is the fact that if the degree is even, if the exponent is even, 2, 4, 6, 8, 10, the sign, whatever's in front of it, stays the same. If the degree is odd, the sign changes. So for our x, negative x to the 4th, it's just going to stay plus 3x to the 4th. Our negative 2 times negative x to the 5th, the negative 2 is going to become positive. Because our negative x to the 5th is going to be negative x to the 5th. And our negative times negative 2 is going to make it positive. And x to the 6th, even degree, is just going to make it x to the 6th. So no matter what the power is, we're used to saying a negative times itself is positive. Any even degree. A negative number to an even degree is going to become positive. Questions on this here? Now, just like the previous time, we're going to go back through and count the number of sign changes. So x to the 6th to x to the 5th, no, positive to positive. 5th to the 4th, no, still positive, positive. 4th to the 3rd, no. 3rd to squared, so 1 squared to our first, x to our constant. So the number of possible negatives that we can have is 3. That's the most we can have, or less than it by an even amount. So 3 minus 2 is. So for this solution here, or this equation here, we could have 3 positives or 1. We could have 3 negatives or 1. Okay? Now to give our answer, we're going to set it up in a table. And the way I set this up is like this here. 2 lines going up and down, 1 going across. And at the top, I put P, N, and C. Well, P is our positives, N is our negatives, and C, complex. So any of our complex numbers, our I terms. Well, the most positives we could have is, the most negatives we could have is 3. Okay. Now the complex, it didn't say anything about it. And the one statement I wrote in was, it's the numbers that are missing. Yes? Well, the degree of our starting polynomial is, so according to the fundamental theorem of algebra, we should have 6 solutions, yes? So looking at the chart, if we had 3 positives and 3 negatives, we have a total of, we should have 6 solutions, yes? So are any missing? No, so the number complex is 0. Because going across, these should always, for this one here, add up to be 6. Now I always decrease the negatives first, because another option we could have is 3 positives and 1 negative. But if I have 3 positives and 1 negative, that is 4. We need a total of, so I'm missing 2. So if there's 3 positives and 1 negatives, there has to be 2 complex. Well, those are the only possible options for negatives, but I could have and 3 negatives, 4, so I'm missing 2. So it could be 1 positive, 3 negatives, and 2 complex. Or our last one would be 1 positive, 1 negative, and 4. And that's it. This here is our final answer. And one thing to note, let's get a highlighter. This column here, our complex, will always be even. It will always be even numbers. Because our complex conjugate theorem we had yesterday stated if A plus BI is a solution, A minus BI is a solution. They always come in pairs. So that column will always be multiples of 2. Either 0, 2, 4, 6, 8 going on. Questions on this here? We ready for the next one? Luckily for us here, they already wrote this out, so we can find positives first pretty easily. So we just go down the line from our 6th power to our 5th power. Yeah, so the first one is true because there's not a sign in front of x to the 6th. It's understood to be positive, so positive negative would be 1. Our x to the 5th to x to the 4th, no, negative to negative. X to the 4th to x to the 3rd would be our second, negative to positive. X cubed to x squared is positive to positive, so no. X squared to x, positive, positive, so no. And x to 9, yes. So the most positives we can have is 3 or less than it by an even amount. So it'd be 3 or 1. Our negatives. And to do the negatives, we're just replacing each x with negative x. And when we simplify these, really, all we're going to do is look at the power. If the power is an even number, the sign stays the same. If the power is an odd power, the sign changes. So our first one, 2 times negative x to the 6. The 6 power is even, so it's just going to stay 2x to the 6. Our next one is an odd power, so it was negative, it's now going to be positive. It's going to change. Our next one is to the 4th power, so the sign is going to stay the same. It's going to stay minus. Our next one is to the 3rd power, which is odd, so the sign will change from positive to negative. Our next one after it, squared, is even, so the sign will stay the same, giving us plus 10x squared. Our next one, plus negative x, is going to go from positive to negative because the exponent, even though it's not written as 1, 1 is odd, so the sign changed. And then we just have our constant term. Questions on how we did this here? Now we just need to count the sign changes. X to the 6, x to the 5th would be no. From the 5th to the 4th would just have a sign change. 4th to the 3rd would not. 3rd to squared would. Squared to x, yes. I think you were looking at the last one. Yeah. And so for our negatives, I don't know why I'm writing out negatives. I didn't write out positives, but that's fine. We also have 3 and 1. So we actually get the same chart. Positive, negative, complex. I always start at the most positive and negatives. Now another way you can look at this and do these here is I start out with the most of each, and then I go to the negatives and start subtracting 2 from it. So positives will stay the same. I'll subtract 2 from the negatives and give us 3 and 1 is 4, so we have 2. Then I'll try to subtract 2 from the negatives. Well, we can't without making it negative. So what I do is I reset the negatives back to the biggest amount and take a 2 away from the positives, which will take it from 3 to 1. That's 4, so we are missing 2. And then I repeat this process again. So I keep subtracting 2 from negatives. 1, 1, 4. And then if I can't subtract 2 from the negatives anymore, I would reset it, take 2 away from the positives. But here I can't take any more away from the positives, so that's it. Questions on this here? Well, I'm going to give us an example of that so it makes a little more sense, because I'm just going to say that there's 5 positives, 4 negatives, and 0 complex. So this is what we're starting with. So I would take 2 away from the negatives, so it'd be 5, 2, and 2. Well, I can do it again, which would give us 5, 0, and 4. Now at this point, I can't take any more away from the negatives. Positives, which would give us 2. Then I do it again. 3, 2, 4. 3, 0, 6. Well, I can't take any more away. 1, 4, 6, 1, 2, 8, 1, 0, 10. Or make sure 5, 4, 5, 3, 4, 7, 8, 9, 5, 9, 9. Here's where there should have been 4. I, for some reason, just assumed it was 6. 6, 8. Yeah, I just got off because it should total 9. But it just keeps doing that. And the reason I like this is that I don't have to keep track of the fact that the number of positives are 5, 3, 1, and the number of negatives are 4, 2, 0, and making sure that I match up every possible combination. This does all the combinations for me, and it makes sure I have them all. Questions on this here? You see another example of possible positive negatives in the complex. Yeah, and this is nice because when we start trying to find zeros and they don't immediately show up on the graph, and we start looking at the rational zeros, it starts eliminating stuff quickly. And that's really what all of these are for. And that's it. And that is the end of chapter 4.